Hello everyone, welcome to lecture 22. Just to recap, in the last lecture we started discussing about the problems of message authentication and message integrity, where the goal of the receiver is to verify whether the message that is receiving is coming from the right sender or not, and to detect whether the message that is received by the receiver is indeed the correct message or not. And we introduced a cryptographic primitive called message authentication code, and we have seen the security definitions of message authentication code, and we also discussed how to construct message authentication code for fixed length messages using pseudo random functions. So, in this lecture we will continue the discussion on message authentication codes, and what we will do is we will discuss how to construct message authentication codes for arbitrary bit strings. So, we will begin with discussing how to construct message authentication code for string of blocks, and this will be further done in two stages. We will first see how to construct prefix free secure pseudo random functions for string of blocks, and then we will see how to convert any prefix free secure pseudo random function for string of blocks to fully secure PRF for string of blocks. And once we have fully secure PRF for string of blocks, we will see how to construct pseudo random functions for arbitrary length input, namely arbitrary bit strings, which will eventually give us message authentication code for arbitrary bit strings. So, that is the plan for this lecture. So, just to recall, in the last lecture we have seen how to construct a message authentication code for fixed length messages using pseudo random functions. So, assume you are given a secure pseudo random function with n bit key, little l bit block length and big L bit output size. Then using the pseudo random function we have seen how to construct a secure MAC where the key space is the set of n bit strings, message space is set of all little l bit strings, and the tag space is a set of big L bit strings. And the construction is as follows: the key generation algorithm outputs a key for the pseudo random function, which is used to authenticate the message by computing the value of the pseudo random function under the key k, with the message being the input block, and that is the tag. And to verify the tag for the message m, the tag is recomputed by recomputing the value of the keyed function f k on the input m and matching whether the recomputed tag matches the received tag or not. If the match happens, then the output is 1, otherwise the output is 0. Now, our goal is to construct secure MACs for arbitrary long messages, because in practice there is no restriction that a message size should be of big L bit. It could be less than big L bit, it could be larger than big L bits, and so on. And it turns out that unlike CPA secure encryption schemes, where if we have a CPA secure encryption scheme for encrypting big L bit messages, and if we want to achieve CPA security for encrypting arbitrary long messages, then we had seen that it sufficed to divide the larger message into several blocks of big L bits and encrypt each block of big L bits using an instance of the fixed length encryption process. But that process of dividing the message and authenticating each block using this fixed size MAC is not going to give you a secure MAC construction. Specifically, assume that you have a message m, right, consisting of 2 blocks of big L bits, and you divide the message m into blocks m1 and m2, and say you authenticate m1 using this fixed length MAC procedure, and you authenticate independently m2 using the same key k under the using this fixed length MAC procedure. Then an adversary who has seen the tag t1 comma t2 for the message m can easily produce a MAC for a new message m dash consisting of block m2 followed by m1, right, and that will be a forgery from the viewpoint of the adversary. So, it is not straightforward to just take this MAC construction for fixed length messages and use it to construct a MAC for authenticating arbitrary long messages. The construction is really going to be a challenging task. So, the idea behind constructing message authentication codes for arbitrary long messages is to look for it should design secure pseudo random functions with arbitrary long bit strings, but fixed size output. Because if we can construct pseudo random functions which can support any arbitrary long bit string as an input and gives a fixed size output, then using such a pseudo random function we can easily construct a MAC for arbitrary long messages. What you basically have to do is you just have to invoke that pseudo random function on the message, which could be of any length, to produce the tag, and as per the idea that we had used for constructing the pseudo MAC for a fixed length message, the corresponding construction will be a secure construction. So, the whole problem of designing secure MAC for arbitrary long messages boils down to the problem of how to construct pseudo random functions for arbitrary long bit strings, and that is what will be the focus of this discussion. So, the reference material for today's discussion will be the chapter from the book draft of by Bonnet and Shoup, and the most of the proofs for the constructions that we are going to discuss in today's lecture will be skipped because the proofs are really advanced. We will be just discussing the overview of the high level ideas behind the security proofs of the constructions that we are going to discuss in this lecture. But if you are interested to see the exact proofs, then you can refer to the lecture given in the book draft by Bonnet and Shoup. Right. So, let us start with the construction of a PRF for arbitrary size inputs from a PRF with fixed size input. So, what you are given is, assume you are given as PRF whose block length is n bits and output is also of n bits, and using this your goal is to basically construct another keyed PRF, which I denote as F star, and which can support input of any length up to L times n bits, and it will give you a fixed output of size little n bits. So, as you can see that the output of the keyed PRF F star which we are interested to construct is independent of the value L, right. So, it does not matter whether your little l is 1, little l is 2 and so on, the output size is always fixed, namely little n bits. So, our goal is how to construct this F star given the keyed pseudo random function f, and we will do the construction, we will design F star from f using a 3 stage approach. In stage 1, what we will do is we will first construct a PRF which will not be operating on arbitrary length input, but it will be operating on arbitrary sequence of blocks, namely it can compute the output for any number of blocks L up to L number of blocks, where each block will consist of n bit of input, and it always gives you an output of n bit, and we call this PRF as blockwise prefix free secure PRF. It will be clear very soon what exactly we mean by the term prefix free secure PRF, but the important thing is that it does not support inputs of arbitrary length, but rather it supports inputs which are actually passed as sequence of several blocks, and it can support inputs consisting of up to L blocks, where each block further consists of n bits of string. So, that is denoted by this notation. That means, each block is of size little n bits and there can be up to little l such blocks. So, the stage 1 will be how to go from this fixed size PRF f to this prefix free secure PRF PF. Then once we have the construction PF, which is blockwise prefix free secure PRF, in stage 2 we take this prefix free secure PF and we construct a fully secure PRF, but which is still blockwise. That means, it can take inputs consisting of up to little l blocks, where each block is of size little n bits and the output is of size n bits. And then finally, in stage 3, once we have the construction f dash, we construct the actual PRF f star which we are interested to construct, which can take any input, any arbitrary bit string as input of length up to little l n bits. So, remember there, so notice that there is a difference between the notation where this notation and the notation where binary string up to length little l n bits. So, when I say input of the form 0 1 raised to power less than equal to ln, that means the input is an arbitrary bit string whose length is ln. But when I say that I have an input of this form, that means my input consists of several blocks, namely up to little l blocks, where each block is exactly of size n bits. So, there is a difference between this notation and this notation. So, that is the 3 stage approach that we are going to follow to construct our required PRF f star from the fixed length PRF f. right, and each of the stages is really interesting and subtle, and we will be skipping the proofs. As I said earlier, if you want to see the proof, you can see the chapter on the in the book draft by Bonnet et al. So, let us begin with the construction of prefix free secure PRF, and for that let me first define what exactly we mean by prefix free set. So, a set Q, which is a subset of set of all blocks up to which is a subset of sequence of blocks up to size L blocks, where each block is consisting of n bits, is called a prefix free set if the following conditions hold. First of all, the set Q should be non-empty, and the second property is that no element in the set Q should be a proper prefix of any other element of the set Q. What this means is that if we have an input member in the set Q, say the sequence A1 comma A2, where A1 is one block and A2 is another block, each of size n bits, then we cannot have the input A1 present in the set Q, because this block input A1 is a proper subset of the sequence of block inputs A1 comma A2. However, we can have the input A2 present in the block Q, because A2 is not a prefix of the block sequence A1 comma A2. So, that is the definition of a prefix free set, right. So, now what exactly we mean by block wise prefix free secure PRF. So, on a very high level, it is a PRF, right, which take inputs as a block sequence, and there could be up to little l number of such blocks, and that PRF will be secure against a weaker adversary, which we call as prefix free adversary. Namely, it will be secure against an adversary or a distinguisher whose queries are restricted to a prefix free set. So, what exactly we mean by that? So, syntactically, block wise prefix free PRF will be a keyed function, and it will take a key of size say little n bits, and it takes a sequence of blocks as input. So, it can take up to little l blocks here, where each block is of fixed size, namely little n bits, and it gives you a fixed size output, say little n bit out little n bit little n bits. And the security property that we want from this block wise prefix free secure PRF is that if we consider a truly random function which also takes input a sequence of blocks, say up to little l blocks, where each block is of size exactly little n bits, and gives you an output of size little n bits, such that the function little f is a truly random function, right, it is a unkeyed function. Then what we mean by a prefix free secure PRF is that the behavior of this keyed PRF should be indistinguishable from the behavior of this truly random function little f against a distinguisher who is restricted to make queries only from a prefix free set. That means, this distinguisher cannot ask for the value of the function on block sequence input A1 comma A2 as well as A1. That means, whatever queries this distinguisher is going to ask in the PRF indistinguishability game, if we denote it by Q, then the set Q of queries for the distinguisher should constitute a prefix free set. So, that is why this distinguisher is a weaker distinguisher or a weaker adversary, because in the actual PRF security definition there is absolutely no restriction put on the nature of queries which the distinguisher can ask during the game. It could be a prefix free set, it may not be a prefix free set. But when I say we are designing a prefix free secure PRF, then it will be secure only against an adversary whose queries constitute a prefix free set, right. So, that is the definition of block wise PRF, which is prefix free secure. And now, let us see a candidate construction which we call as CBC prefix free secure PRF, and the construction is as follows. So, we are given a keyed PRF of fixed size input and fixed size output, and using that our goal is to construct a PRF which is a prefix free secure PRF, right, which can take a sequence of blocks as input, say up to little l blocks, each of size n bits, and gives you a fixed size output. And the way we do it is using the CBC mode of encryption that we had seen earlier with some differences. So, let me demonstrate how exactly this CBC prefix free secure PRF operates. For demonstration purpose, assume that you have a message M consisting of up to 3 blocks, right. Now, to compute the output of the CBC prefix-free secure PRF for this input, what we do is the following. Since we have 3 blocks, we need to invoke the fixed size PRF 3 times with the same key k, and the first invocation of the PRF will be M1 will be with M1 as the input, and whatever is the output that serves as the input for the next invocation, where it is XORed with the next block input, namely M2, and the XOR of the M2 and the previous output of the PRF is fed as the block input for the second invocation, and then we continue the chaining process, and finally the outcome of the last invocation of the fixed length PRFF is treated as the output of the prefix free CBC secure PRF for the message M. That is the way this CBC prefix free secure PRF operates. Okay. So, there are certain differences between the CBC PRF that we have designed just now and the CBC mode of encryption that we had discussed in one of our earlier lectures. So, on your left hand side you have the CBC PRF mode, and on your right hand side you have the CBC mode of encryption, right. For comparison purpose, what I am considering is I am considering a message block consisting of 3 blocks, and how the output of the prefix free CBC PRF will be computed on that message, and on the right hand side part I have the same message, and I am demonstrating how exactly the CBC mode of encryption will be operated on the same message, right. So, the differences between these two primitives are as follows. First of all, when we see the CBC PRF, then the intermediate values, they are not output at all, right. It is only the final outcome, it is only the outcome of the final invocation of F which is output as the overall output of the CBC PRF. Whereas, in the CBC mode of encryption, each of the intermediate outcomes of the F are also part of the overall output. This is because in the CBC mode of encryption the goal is to encrypt each of the individual blocks. So, that is why we need to definitely output the intermediate outputs of the PRF. But when we consider the CBC PRF, our goal is to compute a fixed size output for the overall message. So, that is why it is not necessary to output the intermediate output of the intermediate invocations of the PRF. So, that is the first difference. The second difference is that if we consider the CBC PRF, then it uses a fixed IV, namely in the picture there is no IV at all, but you can always imagine that the IV is set to all zeros, which is publicly known. But when it comes to the CBC mode of encryption, then there is an IV and which is randomly selected for each instance of the CBC mode of encryption. So, you can imagine that CBC PRF uses a deterministic IV which is always fixed for every message, but when it comes to the CBC mode of encryption, IV is selected independently for each invocation. So, these are the two differences, and it turns out that if you actually modify the CBC PRF by also outputting the intermediate outputs of the PRF, then the overall PRF is not a secure PRF. Also, instead of using a fixed IV, if you start using a random IV, there is no guarantee that overall the CBC PRF is indeed a prefix free secure PRF, right. So, that is how the CBC PRF operates, and I will not be going into the security proof that why exactly this CBC PRF is indeed a prefix free secure PRF, but let me give you an intuition that why it may become insecure if we do not restrict our adversary from making queries which constitute a prefix free set, right. So, what I am going to do is I am going to demonstrate the insecurity of the CBC prefix free secure PRF against an adversary which can make queries which does not constitute a prefix free set. So, imagine that adversary, there is an adversary which queries for a block input A1 and gets the output Y under an unknown key k which is not known to the attacker, right. So, the way output Y would have been computed is as follows. Since we have only one block, basically we would have evaluated the fixed length PRF F on the input A1 with the key k, and that is how the output Y would be computed. Now, imagine adversary has a new block, a new input consisting of 2 blocks, say block A1 followed by block A2, where A2 is a special block here. A2 is related to the block A1 and the output Y, which is the value of the prefix free PRF on the block input A1. And now let us ask what exactly will be the value of this prefix-free CBC PRF on the input A1 comma A2, right. So, this is how the output of the CBC PRF on the input A1 comma A2 will be computed, right. We will have two invocations of the fixed length PRF, we will do the chaining and the final output will be this. Now, what exactly is the outcome of the first invocation of the PRFF here? It is Y, because that is what is this structure, right. So, you can see that if I just focus on this part here, this part is nothing but the computation of the CBC PRF on a different input consisting of just a block A1, and we know that that is nothing but Y. And now this Y is fed is fed as the input for the second invocation, where this Y is XORed with the next block here, and the next block is A1 XOR Y. So, the effect of this Y and Y cancels out, and what basically we are doing here is we are actually invoking the fixed length PRF on the input A1, and adversary already knows that the value of this PRF under the unknown key K, but with the known input A1 is going to give you the output Y. So, adversary already knows that the output of the CBC PRF on the input sequence A1 comma A2 will give you Y if the block A2 satisfies this relationship, and that gives him an advantage or a strategy to distinguish this CBC PRF from a truly random function, right. So, what the adversary basically can do is it can first ask for the function output on the block input A1, and then it can ask for the function output on the block sequence of block inputs A1 comma A2, and it can compare it with Y. If it sees the output of the function input on the sequence A1 comma A2 to be Y, then it knows that it is interacting with a prefix-free CBC PRF, and if the output is not Y, that it means that it is interacting with a truly random function, and it can be formally proved that the distinguished advantage of the distinguisher is significant, right. So, that means if we are allowing adversary to query if the set of queries which the adversary can ask does not constitute a prefix-free set, then definitely the construction that we have seen now is not secure, right, because in this particular example he is asked to query for A1, and then he is asked to query for also the input A1 comma A2, and clearly A1 is a prefix of the set A1 comma A2. But the definition of prefix-free secure PRF is that it is secure only against an adversary who cannot query for both A1 as well as the input sequence A1 comma A2, right. So, that is the basic intuition that why this chaining PRF is a secure against a prefix-free adversary. If we do not put that restriction, then definitely it is distinguishable from a truly random function. So, now we have a candidate block-wise prefix-free secure PRF, and what we do is now we will go to the stage 2, where we will convert this block-wise prefix-free secure PRF to get a fully secure PRF, where there is no restriction whatsoever on the queries which the distinguisher can make in the PRF indistinguishability game, right. So, you are given this, we have already seen a candidate for this, namely the CBC PRF block wise, and our goal is to construct a fully secure block wise PRF which can take sequence of blocks as input, say up to little l blocks, where each block is of fixed size, say little n bits, and the output is a fixed size output of size little n bits. And there are several approaches for doing this. There are several approaches from going to this prefix-free secure PRF to a fully secure PRF, and each approach has a different trade-off. So, the first approach is an encrypted CBC PRF, and remaining two approaches are deterministic prefix-free encoding and via randomized prefix-free encoding. So, what this the last two method, what it does is basically it encodes the input of your block-wise prefix-free secure PRF in such a way that the resultant encoded inputs constitute a prefix-free set, whereas the encrypted CBC uses two keys, where using the first key we operate the prefix-free PRF, and then the output is again encrypted using the second key, which ensures that adversary is confused. So, let us go deeper into the different approaches. So, let us first see how we construct the block wise prefix-free secure CBC to a fully secure CBC using encryption. And the idea here is to use two independent keys, where using the first key we operate the prefix-free blockwise CBC, and using the second key we encrypt the output of the blockwise CBC. More specifically, what we are going to do is we are going to construct a new PRF, which I denote as FCBC, which is fully secure. There is no restriction on the distinguisher. It can make queries which may be prefix free set or which may not constitute a prefix free set, and so on. So, the construction is going to take two keys, and the PRF can support a sequence of blocks, say up to little l blocks, each block consisting of fixed n bits. And I stress that here throughout this discussion, this little l is some polynomial function of your security parameter, and the output of this blockwise PRF is going to be of little n bits, right. So, how exactly the operation will happen here? Since the key is of size 2 n bits, we parse it as sequence of 2 blocks of n bits each, and we call the first part of the key to be K1, and with K1 we actually first run the prefix free CBC, right, which operates blockwise, and this will be the output of the prefix free CBC PRF with respect to the key K1. And once we obtain the output, we use the remaining part of the key, which is also of n bits and independent of K1, and we use this key to again encrypt the output that we have obtained from the prefix free CBC PRF, and that will be the overall outcome of this fully secure CBC PRF with respect to the key K1 comma K2, right. So, there are several advantages as well as disadvantages for this blockwise encrypted CBC PRF. The advantage here is that this PRF constitutes what we call as a streaming PRF, and which further gives us what we call as a streaming MAC. So, remember our goal is to basically construct PRF supporting arbitrary block size input. Our goal is to construct PRF which can take inputs of arbitrary size. So, right now what we are aiming is we are aiming to construct PRFs which can take sequence of blocks as input and gives you a fixed size output, and once we have such PRFs we can always use those PRFs to obtain the corresponding secure MACs, namely a MAC which can take inputs, which can take sequence of blocks as input and give you a fixed size tag. So, the advantage of this encrypted CBC PRF is that it constitutes what we call as a streaming MAC. Namely, in this construction the length of the message need not be known in advance, right. That means, imagine a scenario where a sender is continuously sending message packets to the receiver, and it does not know exactly what is going to be the length of the message m. That means, it does not know well in advance up to how many blocks of little n bits will be there in the message m. What it knows is that maximum number of blocks that can be there in the message m is L, where L is publicly known, but apart from that it has no knowledge whatsoever about the exact number of blocks. So, if you see the way this encrypted CBC PRF is operating, the length of the message is not at all useful here. So, as and when new blocks are coming, right, what the sender can do is basically it can compute the corresponding output of the CBC prefix free CBC PRF, and once the message is over, that means once the last block of the message is coming to the sender, it can compute the final invocation of the PRF with respect to the key K2. So, that is why it constitutes what we call as a streaming MAC, because the length of the message need not be known in advance here. The disadvantage in this construction is that we now need to operate with two keys. That means, the overall key for the CBC blockwise PRF actually consists of two independent chunks of n bits each, and we also need an additional PRF invocation, namely the final PRF invocation apart from the number of PRF invocations which we are invoking internally as part of the prefix free CBC PRF. So, these are the two disadvantages, and we also have an advantage here, right. So, you have the trade off here. If you want a streaming MAC, then this really is a very good construction, but you need to pay something for that, namely you need to operate with two keys, and you should be willing to have an additional PRF invocation here, right. I hope you enjoy this lecture. Thank you.